more. So today's topics are going to be privacy and then, or rather minimax rates under privacy constraints, and then a little bit about computation constraints. So for privacy, the references are Acharya, Sun, and Zhang, Differentially Private, Aswad, Fanos, and Likham, paper from 2020. And the second one is by Ducci, Jordan, and Wainwright. It's called Minimax Optimal Procedures for Locally Private Estimation. And it was published in 2018, but I think it's actually from 2013. So historically, the second paper is several years before the first one, but the first one focuses on the general setting of what's called epsilon delta differential privacy, whereas the second one focuses on local differential privacy. So that's why I'll talk about the first paper first. And actually, I might end up spending most of the time talking about the results in the first paper, but we'll see how time goes. So let's begin with some reminder definitions about differential privacy. Okay, so the standard definition of differential privacy is the following. Let script X denote the underlying data domain of individual data samples. And a randomized estimator, data hat, which maps script X to the n. We have n data points to theta. Satisfies what's called epsilon differential privacy, which we'll also abbreviate by epsilon dp, if for all subsets S of capital theta and all data points X or data sets X, Y in script X to the n with Hamming distance 1, we have probability data hat of X is in S is less than or equal to e to the epsilon times probability that data hat of Y is in S. Okay, so differential privacy is sort of inherently a probabilistic definition. So we can think about theta hat as some randomized algorithm, and in practice, you can think about it as some, I mean, in some settings, you might take an empirical mean of the data and add some noise to it, for instance. And what we want to do is we want to guarantee that, that the probability that the output of the algorithm is in some set S doesn't change too much if we just perturb 1 point. So that's what it means for X and Y to be of Hamming distance 1. So it's also some notion of stability of the algorithm. And there's also a version of differential privacy that's called epsilon delta differential privacy. And maybe I'll just write it here. So we're not going to talk about this because it just makes things more complicated. But there are, in fact, results under epsilon delta differential privacy in this work. So epsilon delta differential privacy is where you also have an extra term delta there. So there's an additive term that gives you a little bit more slack. Okay, so we're interested in minimax risk under the constraint that an estimator is differentially private. So just to make this explicit, so for a collection of distributions, the definition for a collection of distributions P, we want to characterize the minimax risk, which we'll write as R sub dp for differential privacy of P L epsilon, which is the infimum over, let's say theta hat is epsilon differentially private, supremum over distributions P in script P, expectation x distributed as p to the n, L of theta hat of x, theta of p. So this is using the same notation that we had last time. Let me just note here that here we're assuming that we have n IID data points. Okay, so we'll be constructing an estimator based on n IID data points. And just to remind you, at the very beginning of the first lecture, we were working under a setting where x can come from a general distribution. But throughout this work, we'll assume that our data are IID. Okay, so maybe just a quick remark is that the usual minimax risk, which I guess I didn't denote as anything. So usual non-private minimax risk is always a lower bound for R sub dp p L epsilon. So I'm just stating the obvious. And this is simply because we're restricting to a class of estimators theta hat. So of course the infimum will be at least as large as it would have been with no restriction. And we'll use that in some of the lower bounds. Okay, so now what I'm going to give is a differentially private version of Fanos method. Okay, so this is Fanos method for differential privacy. And we have the following theorem, and this is from the paper by Acharya et al. So let script V be equal to a set of distributions, which is a subset of script P. And let this be such that for all I not equal to J, we have two conditions. So the first one is that we have some notion of separation, theta of Pi, theta of Pj is bigger than or equal to 2 delta. And the second one is that the total variation distance between Pi and Pj is at most gamma. I forgot to mention that we're going to use the same convention as earlier, and we're going to assume that this L here is equal to, oops, sorry, hit the wrong button, is equal to phi composed with rho. So as before, rho is the semi-metric, phi is the increasing function. So we need, just as in the earlier development of Fano, we need 2 delta separation in the rho metric. And now we're, instead of this mutual information or KL divergence upper bound, we're going to have a total variation upper bound. And remember, this is just on the distribution of the data, these are the distributions that are generating the IID data points. And the conclusion is then R sub dp of script P L epsilon is bigger than or equal to some constant times phi of 2 delta times the minimum of 1 and m over e to the 10 epsilon n gamma. Okay, so we have this lower bound, and of course, as in the case of the usual Fano, there's some prefactor that depends on delta. There's also a dependence on how large a set we can have, a 2 delta separated set. We see this, but the difference here is that before we had an upper bound on something like KL divergence, and here we have an upper bound on TV, and that shows up down below in the denominator. And in practice, the game we would play is kind of like in the usual Fano method. We would try to lower bound this stuff by some constant. Okay, so we would, maybe I should write this a bit more carefully. Let's do this. So what we would want to do is construct P1 up to Pm, then choose delta such that, so choose delta and the packing set. P1 up to Pm such that this is bigger than or equal to some constant. Okay, so I guess there's not explicitly a dependence here on delta, but everything is of course all connected to each other. And you'll see this in the examples, or in the one example. Okay, so now let's go to a discussion of the proof. I think I'll go through most of the details. Okay, so the main statement, or one useful statement which I'm not going to prove, is the following. So one can show that under condition B, there exists a coupling xy between the n-fold product distributions, pi to the n and pj to the n, such that the expected Hamming distance between x and y is equal to n times the total variation distance between pi and pj, which is then going to be less than or equal to n gamma, because our assumption is that we have this upper bound on the TV distance. Okay, so really, as we'll see, what we need in order to have guarantees for differentially private algorithms is some control of what the Hamming distance is. And this sort of makes sense because differential privacy tells us how an estimator behaves when we change one item of the data set. And if the Hamming distance is bounded by n gamma, then really we have a bound that's something like, well, whatever we incurred every time we changed one element of the data set and then iterated n gamma times. So let's keep going. So just to commemorate this event, so by Markov's inequality, we then have probability that the Hamming distance between x and y is bigger than 10 n gamma, will be at most 1 over 10. So let E be the high probability event. So this is going to be the event that the Hamming distance is less than or equal to 10 n gamma. Okay, so let's save that for later. All right, so now note that for any differentially private estimator, theta hat x, if we define the production estimator, p hat of x is equal to the argmin over all p in our set of rho of theta of p, theta hat of x, then the triangle inequality implies that we have the following bound: rho of theta of p hat, theta of p is less than or equal to rho of theta of p hat, theta hat of x, plus rho of theta of p, theta hat of x, which is bounded by twice rho of theta of p, theta hat of x. Okay, so what's going on here? So if you remember when we proved Fanos inequality before, or Fanos method before, we dealt with this sort of projection estimator, although it wasn't exactly called that. So just, I think what so earlier, I'll just write this in red, we defined something like, I think it was psi of x was the argmin over all of the indices, rho of theta hat of x, pi. I think that's what it was. And now we're replacing it with this, which is mapping, which is giving us the actual, it's denoting the actual distribution, which is the closest to theta hat of x. So to draw a picture like we had in the last lecture, we have this, well, we have this, maybe I'll do this in black. We have these points that correspond to theta of P1, theta of P2, up to theta of PM. And we know that by construction, these are all 2 delta separated. And then what we see is theta hat of X, okay? And we look at the closest guy in row distance. So in this case, P hat of X would be equal to P2. Okay, so we're just sort of mapping things to the closest guy. And just for bookkeeping purposes, rather than picking out the index, in this case 2, of the closest theta, we're actually picking out what the P would be. Now this inequality follows quite easily. So the first one is triangle inequality. And the second one is telling us that, well, this quantity is the same as this quantity. And then by optimality of P hat, this quantity is also less than that quantity. Okay, so what are we going to do with this? Well, now we are going to start playing around with expected values and probabilities. So let's go back to the notion, to the expectation that shows up in the minimax risk. So you're right. Therefore, supremum over P in script P of expectation x distributed as P to the n of L of theta hat of x, theta P. So this is what we're interested in. We're interested in this quantity where theta hat is a differentially private estimator. Well, by Markov's, So first we're going to lower bound this by an average. So this is just like in the usual Fanos inequality. Supremum is certainly lower bounded by an average of some specific instantiations, which correspond to the PIs that are in our set. Okay. And then now I'm going to take 1 over 2m. So right up here, we have an inequality that relates these guys to these guys. So I'm going to use that inequality here. This is greater than or equal to sum P in V, expectation under x distributed as Pn of L of theta of P hat, theta of P. Okay, so of course, this inequality here is in terms of the rows, but if we apply the function phi, then actually, is that true? Okay, well, I will have to go back and look at this myself. So certainly, if there's no phi function, it is true. So if this, let me correct myself and then maybe erase it. Okay, so if this were a row instead, and if L were equal to the composition of phi times rho and there were no rho, right, then this would be a row, and I could certainly use this inequality up here to include this step here. However, if I try to apply phi to both sides, then I may have a little bit of a problem because 2 is showing up in the wrong place. Oh, someone's telling me over chat that it works if phi is increasing. I'm not sure if it works if phi is increasing. Okay, well, let me go back and edit my notes later. But to be honest, the way that this was presented in the paper, there is no phi function. And the example we're going to use, there's only a row. So later we're going to apply it where the loss function is just the total variation distance, and then we don't need the presence of phi. But when I was preparing the lecture, I thought it would be nice if, okay, the person who said that they thought that it was immediate is said that maybe it's not. Okay, so when I was preparing the lecture, I wanted to prove this in as much generality as I did in the earlier parts. So I added a phi, and I think that this might not immediately follow, but probably some version of this should work if the loss function is phi times rho. So maybe for now, let's assume that L is a semi-metric. So we'll assume that L is a semi-metric and rigorously proceed. And I will look back and see if I can fix this later. Okay, good. So assuming that this inequality holds where rho is equal to L, then we can go from here to here because we just take out a factor of 2. Good. And then what? So now we're going to use Markov's inequality and say that this is greater than or equal to. So now I'm going to drop all the phis that I had earlier. So let's say 2 delta over 2m, sum p in script v of probability under x distributed as p to the n of L of theta of p hat, theta of p bigger than or equal to 2 delta. Okay, so this is just Markov. And then this is equal to delta over m times the sum p in script v probability. Okay, well, I don't need that step, let's just say this is equal to this probability x is distributed as p to the n, p hat of x is not equal to p. Okay, and why is this true? Well, this is actually sort of obvious. So remember that that p hat is going to be one of the pi's, right? Or sorry, one of the p's that is in my 2 delta separated set. And so theta of p hat is either going to be equal to theta of p, or it's going to be something that's further away. Okay, let's write this in words. So simply that the set rho of theta of p hat, theta of p less than 2 delta is exactly equal to the event that p hat is equal to p. Okay, so I mean, you either map it to something that's not p, or you map it to something that is p, and if you map it to something that's not p, then you go 2 delta away. Okay, good. So now what do we want to do? Well, we want to derive a lower bound on this left-hand side, so it remains to derive a lower bound on this guy. All right. Okay, so there's a little bit more manipulation here. So let beta I be equal to the probability under x distributed as pi. P hat of x is not equal to p. So we want to lower bound the sum I goes from 1 to m of beta I. Okay. So if we do that, then we'll lower bound this guy as well. All right. So now for a fixed pair, pi pj with I not equal to j, let xy be the coupling mentioned above. So it's this coupling so that the Hamming distance between x and y is going to be small with high probability. Okay, then we're going to write a little bit more algebra. So 1 minus beta j. So beta I is, in words, it's the probability of error when we draw our data from the distribution I. This is equal to the probability under y is distributed as pj of p hat of y equals pj. Okay, so here, just to keep a little bit better track of the notation, so x and y are denoted as pi and pj. So when I write out 1 minus beta j, I'm looking at the probability of being correct when I'm drawing from distribution j. So that's why I'm putting a y there. We can write this as a sum over states little y, probability that y takes on state little y, probability that p hat of y is equal to pj. And now we're going to focus on when the event, the high probability event holds and when it doesn't. Okay, so the high probability event was denoted as E. This is when the Hamming distance is close. So we'll look at p of x comma y, probability that p hat of y equals pj, plus the sum. And now we just don't care when things are not in E, so we'll just have probability of x, y. If you're following very closely, then you will wonder perhaps why there's a probability here. Here, y is a particular instantiation of the data, and you might wonder why there's even a probabilistic statement, and this is because, well, p hat depends on theta hat. It's a projection of theta hat applied to the data. And theta hat itself is a randomized algorithm through our definitions of differential privacy. Okay, so if you're following thus far, then what do we know? Well, we know that this guy is upper bounded by 0.9 because 0.1, because by our earlier high probability event, we had defined it so that the probability of E not happening was bounded by 1/10. Okay, so then this implies that probability that the sum xy in E, p of xy, probability p hat of y equals pj is going to be at least 0.9 minus beta j. Okay, And then we have probability x distributed as pi of p hat of x equals pj. So now this is the probability of being incorrect. So remember, I is not equal to j, so we're saying that we're drawing the data from I, and we're concluding that we have j. Well, this is bigger than or equal to the sum over xy in e, p of xy, probability that p hat of little x is equal to pj. So again, I'm just now summing over all of the possible instantiations of the pairs xy, and I'm ignoring the ones that aren't in e. And I have here, so I have here a lower bound on something that looks very similar, right? I mean, this sum looks almost like that one. And the difference is that now instead of y, I have x. But now here's where we use the fact that we have differential privacy. So this is in turn bigger than or equal to the sum over xy in e, probability of xy. And here we have an e to the negative 10 epsilon and gamma times probability p hat of y is equal to pj. Okay, so what have we done? Well, we've changed the x into the y, and we use the fact that they're in e, so they have Hamming distance at most 10 and gamma, right? And then by differential privacy, every time we change one data point, then we can change the probabilities by at most e to the negative epsilon. Okay, so then this is going to be bigger than or equal to, now using this bound here, bigger than or equal to 0.9 minus beta j e to the negative 10 epsilon and gamma. Okay, so then the last manipulation. So remember, we wanted to get a bound on the summation of beta I, right? We wanted to get a bound on this summation, on the probabilities of errors. Instead, we have here a lower bound that looks like that. So we just need to rewrite things a little bit. So finally, we have sum I goes from 1 to m, beta I, which is equal to the sum I goes from 1 to m, probability under x distributed as pi to the n of p hat of x not equal to pi. So that's just the definition. And we can write this as a double sum over I goes from 1 to m, and sum j is not equal to I, probability x distributed as pi to the n, p hat of x is equal to pj. We're writing it like this because we want to invoke this guy there. And this is going to be bigger than or equal to the sum. So if we sort of switch things around, j goes from 1 to m times the probability that we're not equal. And we'll be summing up the same lower bound here, m minus 1 times. So we end up with this times 0.9 minus beta j times e to the negative 10 epsilon and gamma. Okay, so now we have this summation of beta I on one side, and we sort of have the summation of beta I again. And if we rearrange, then we end up with the final result. So rearranging gives the desired lower bound on summation of bi, implying the result. Okay, so it was a bunch of manipulation. So let's just go back and review what we've learned, or what was happening here. So we go back to the theorem, and so, well, if you, with my edits, I guess this is now going to be replaced by row, but I'll go back and see whether something more general can be said. So what we did was we saw that if we had a 2 delta separated set in the row semi-metric, and we have total variation distance of pairs bounded by gamma, then we could use the fact that there's, well, with high probability, there's a coupling such that with high probability, x and y are close to each other. And we can use that then to deal with these probabilities of error that show up in applying the usual lower bounding techniques for the quantity here that's showing up in minimax risk. Okay, so let's forge ahead and discuss an example where we're going to use this. So the example that we'll look at is for k-ary distribution estimation. Okay, so consider the problem of estimating a density of a distribution supported on k points. One up to k, and let script p be the k-dimensional probability simplex. And suppose L, which is now equal to rho, is the, or I'll just write it like this. Suppose L is the TV distance. Okay, and so in particular, L is a semi-metric. So we can ignore C. So even if there's not an easy fix to the manipulations I was trying to do above, that's okay. We can still apply the theorem and not be missing any rigor here. Okay, so we will show that the differentially private minimax risk is lower bounded by order of square root of k over n max with k over n epsilon, provided k is bounded by some constant times n epsilon, using Fanos method. Okay, so here you see that we have a max between two quantities. One of them involves the privacy parameter and one doesn't. And this looks a bit like the types of rates that we saw in the robustness lecture, where we had one part that depended on the problem parameters and one part that depended on how much noise we wanted to be robust to. And this is no accident. Really, the first bound can be obtained using the usual Fanos method with no privacy constraints, because as we said, that's always a lower bound on our differential privacy. And then the second one can be obtained using the method that I just described. Of course, even for the usual Fanos method, you need to construct some sort of well-separated set. And we'll use the same separated set with slightly different parameters to get both lower bounds. So let's see how this works. So we will use the following lemma. So here's another result from coding theory. And this lemma says that let 20 less than or equal to L less than or equal to K over 2 be an integer, then there exists a constant weight binary code C of length K such that, of length K, weight L, and minimum distance L over 4, with the cardinality of C being at least K over 2 to the 7/8 L to the power 7L over 8. So we're not going to prove this. What does this mean? So we have a binary code, so the values are 0 and 1, length K. Weight L means that the total number of ones in each of the code words is equal to L, and then it's going to be separated. Every two code words have having distance of at least L over 4. So we're going to apply this result. So we will apply the lemma with L equals K over 2. Okay. So I guess for this, technically for this result to hold, we'll need K to be at least 40. So we'll say that this lower bound should hold as long as K is larger than some constant. Okay, so we're going to go about and construct our two delta separated set based on such a set of codes. So suppose delta is less than 1/16. So delta is the parameter that we're going to play with later to balance things out. Now, for each C in the code word in the code book, we define the k-area distribution with PC of I. So we're defining a density on I points. So it's 1 plus 16 delta over k if Ci is equal to 1, and 1 minus 16 delta over k if Ci is equal to 0. Okay, so we have, of course, C is going to be equal to some binary string. And this is just telling us that on average, all of the points, well, the density that we have for all of the k values is 1 over k, but then we have a little bias upward and a little bias downward. Okay, and this actually defines a density. It integrates to 1 because we're using L equals k over 2, right? So L equals k over 2 means that, well, the weight is L, so that means that every code has exactly the same number of ones as zeros, and I guess it actually works in this case. Okay, so we define this density, and we have the whole code book script C, so we end up with a whole bunch of different densities. And now we want to show that these are in fact going to be 2 delta separated, and also that we have an upper bound on total variation distance. Okay. Oh, so someone asked on the Zoom, is it easy to calculate differentially private estimators that match the risk bound? So I forgot to mention it before I dug into the proof. So usually the pattern that I've been doing where I've been discussing these results is that first I state the lower bound and then I say it can be achieved. So let me just put a note here. This can be achieved using what's called a Laplace mechanism. Okay, so following the pattern of not going into detail about anything with upper bounds, let me just say that Laplace mechanism is where you add Laplace noise to an estimator in various ways in order to make it differentially private. So what you do is you look at the histogram of your data, and then you add some noise to it according to the Laplace mechanism. So yes, it can be achieved. Okay, so going back to this construction, so now we need to check that we have a 2 delta separated set. So of course, let our set be equal to PC such that C is in script C. Then for C not equal to C prime, we need to show separation in row metric. Our row metric is total variation distance. And we need to look at PC and PC prime. And this is equal to, so for discrete distributions, it's just 1/2 the L1 distance. I goes from 1 to K, PC of I minus PC prime of I. And then you can just sort of look at the separation between the two distributions. And I believe you'll get 1/2 times 32 delta over K times K over 8. And this is all coming from the fact that, well, the 1/2 is, of course, the 1/2 there. And then whenever the coordinates differ, the difference between PCI and PC prime I is going to be twice of 16 delta over K, which is this guy. And then the minimum distance is at least L over 4. L was K over 2, so we get that. Okay, so we defined everything, of course, so that this would be exactly equal to 2 delta. Good, so we have 2 delta separation, but now we also need an upper bound on total variation. Fortunately, that's also easy. So we also have total variation between PC and PC prime is upper bounded by 1/2 times 32 delta over K times K. And where is this coming from? Well, again, whenever the coordinates differ, they differ by 32 delta over K, and the length of the codes is K. So they can differ in most K components. And this is equal to 16 delta, which we'll define as gamma, because we wanted an upper bound of gamma between pairs of, for the total variation distance between pairs of distributions. Okay, so, and then by the lemma, on how big this code book can be, we have, or we can choose script V such that log base 2 of m, or just log of m, is on the order of C times K. So the lemma tells us that the size of the code book is this. So the log of that will have we'll have 7L over 8, which is order of K, times the log of this guy. Of course, K and L are the same order, so it's really a constant times is log of a constant times order k. So that's why we have order ck. Good. So now we're ready to plug it into our bound. So so the Fanos method bound then gives r sub dp of p L epsilon is going to be order of. So we have our delta. So maybe I'll just scroll up and remind you what the bound looked like. So the bound said that we have some constant, we have a delta, and then we have a min of 1 and m over this stuff. Okay, so let's go back down. So we have this thing times minimum of 1, and we have to look at m. M is equal to, is on the order of ck, and then we have e to the n 10n epsilon gamma. So so 10n epsilon gamma becomes c prime epsilon n delta. Okay, and that's because delta was the same order as gamma. Okay, so we had 10 epsilon n gamma becomes c prime epsilon n delta. Okay, so as I said, we want to choose things so that this stuff becomes a constant, and clearly we can then choose delta to be on the order of kappa of k over epsilon n, leading to omega of k over epsilon n bound. Okay, and that's the bound that I claimed from the beginning. Now we need to get the other bound as well. So up above, I also had an order of root k over n, which I said could be obtained using the usual final bound. So to obtain the omega k over n bound from usual final, we will reuse the same construction. With a different delta. Okay. So so we're going to have the same construction here, and we're just going to tweak the parameter that tells us how much we change these distributions by. So we have this 2 delta separation, so that's good. We still have it. Now what we need is a bound on the pairwise KL divergences, right? Because that's what we have instead of TV, we need KL. So we have, or let's just say, for C not equal to C prime, we have KL divergence between PC and PC prime. So it turns out that the KL divergence is actually upper bounded by what's called the chi-squared divergence. And this can be written out quite nicely as a sum I goes from 1 to k, PC I minus PC prime I squared over PC prime I. And it turns out that this is order of delta squared. So why does this make sense? Well, remember that the difference between the coordinates when there is a difference is on the order of delta. So really the numerator is sort of order of delta squared. And then for the denominator, all of the components are kind of roughly equal to 1 over k. Okay, so you can show this, and then Fanos method gives the bound. So we have omega of, well, what should show up? We should have delta, and we should also have 1 minus the upper bound on the pairwise KL divergences, c times n times delta squared, because we have a product distribution, plus 1 over log of the size of the packing set. Remember, the size of the packing set was log of m is c times k. So we have down here c times k, and that means that if we want to make this this stuff bigger than or equal to 1/2, then we can choose choose delta squared to be on the order of k over n. So we get to the bound of omega of root k over n. Okay, so all is well. Good. Okay, so not surprisingly, this took up a big part of the lecture. So now I'm going to say something about local differential privacy. So my plan is to talk about this for, let's say, the next 15 minutes. Then we'll have a break. Then I'll talk about local differential privacy for a bit more time, and then switch over to computation, because the computation section is a little bit shorter than the others. But I think I will probably still end up skipping a bunch of details, because local differential privacy gets pretty, well, it is pretty detailed heavy, even in the presentation I tried to put together. So what is local differential privacy? So just a sort of a brief motivation and a sketch. So the setup of usual DP assumes that a central curator collects all data X and computes data hat X by adding noise, or let's say by randomization. Okay, so maybe the important part is a central trusted curator. But individuals, or let's just say, but what if individuals don't trust a central curator? And are only willing to release a noisy version of their observations, of their data. Okay, so the picture to have in mind, this is sort of graphical model speak. So you have your data sets, your data points, x1 up to xn. So these are what your individuals have. And they want to release some version of their data, Zn. So this is sort of the privacy wall. They don't want anyone to see what their xi's are, but they'll release these zi's, and then the estimator is going to be based on the zi's. So the final estimator is going to be some theta hat of z1 up to zn. The most general local differential privacy setting allows these z's to depend on each other. Okay, so there's going to be possible dependencies as you go along. So let's give a definition, a more rigorous definition. So here's the definition. For a privacy parameter alpha bigger than or equal to 0, the random variable zi is alpha locally differentially private for xi if for all possible z1 up to zi minus 1, so those are the previously released observations, and for all x prime in x, those are your possible values of x, we have supremum over S in some sigma field over the space of Z, Q of Zi in S, given Xi equals X, Z1 equals Z1 up to Zi minus 1 equals Zi minus 1, divided by the probability that Zi is in S, where now we change the value of X to X prime, and everything else stays the same, is bounded by e to the alpha. Okay, this is where this guy is an appropriate sigma field. And so this is what it means for Zi to be a private view of Xi. And then, of course, the algorithm is going to be anything that operates on the Zi's. So an estimator Q of Z is, I guess I mean, let's say theta. An estimator theta hat of Q of Z is locally differentially private if each Zi is alpha locally differentially private. Okay. And so actually, to make things simpler, oftentimes people focus on what's called the non-interactive mechanism. So a non-interactive mechanism is where we massively simplify this diagram. And we say, well, it's great that that the individuals could use the publicly released ZIs that have come before to create their privatized versions, but why don't we just assume that everything's independent? Okay, and that doesn't mean that these guys are necessarily IID. The original X's were IID, and then we're just generating some sort of noisy versions. So this version where the ZIs are independent given the XIs is known as the non-interactive mechanisms. Okay, so the definition is definition here is a non-interactive estimator satisfies alpha local differential privacy if the supremum over all S and the supremum over all X prime of, now we just have to condition on the value of Xi. Zi in S given Xi equals X prime is bounded by e to the alpha. Okay, so this looks a little bit, this definition looks a little bit more like the usual differential privacy, right? We change one value and we don't want the estimator to change too much. So now we change one value and we don't want the corresponding Z to change very much. I'm not going to dwell on these definitions much longer, but let me just say that, after you've seen these definitions, you might wonder, well, what's up with all of this, possible dependencies? It makes perfect sense that everyone just generates their own data. So one example of sequential mechanisms that are studied are when these might correspond to, if you're trying to do some sort of stochastic gradient descent, and each time you draw a new sample and you use that for optimization. So you could think about the ZIs as being the previous iterates. So in order to get the next iterate, you draw the new, you draw a privatized version of the new data, but you use the previous iterates to continue to update. But let's not dwell on that. So for the results that I'm going to state and use, we'll focus on just guarantees for non-interactive mechanisms. Okay, so so now with a little bit of notation, let script Q sub alpha denote the set of all conditional distributions with the alpha locally differential private property. And we can define the minimax risk as R sub LDP of P L alpha. So now our privacy is parameterized by alpha rather than epsilon. This is going to be the infimum over theta hat and over Q, which is in this set of possible conditional distributions Q alpha, supremum over P in script P, expectation over X distributed as Pn. So we have IID data, and conditionals of Z given X come from Q. And then we have a loss of theta hat of Z. Let me move this over. Right here, comma theta of P. Okay, so let's just sort of stare at this a moment. So we have the loss function applied to the thetas, and now theta hat is a function of Z rather than X. We take an expectation with respect to X as well as the way that we're generating the Z's from the X's. We're allowed to design this channel Q however we want to generate Z's from X's, as well as the estimator theta hat. Okay. And maybe the one thing to remark is that unlike in the usual privacy, in the bounds that we talked about earlier with not local, but just epsilon differential privacy, in those cases, the usual non-private risk was a lower bound. That is no longer necessarily going to be the case here, right? Because now we have estimated as functions of Z rather than X. So it's not like we're just taking an infimum over a smaller set like we were doing in the case of differential privacy constrained estimators. Okay. And I should say that, so this work I'll mention is from Ducci et al.'s paper. And they do study a little bit non-interactive mechanisms as well. We're focusing here on interactive mechanisms and Fano to make the explanation a bit simpler. So we're going to talk about Fano's method. So consider, of course, a set of distributions PV such that V is in some script V, which is a subset of P. And now, so now to make things even more complicated, we will use a distance-based generalization of Fanos inequality. And rather than having to construct a 2 delta separated set, subset of script P, we will let script V be an arbitrary finite set. Okay. Or I guess what I mean is we'll let this guy, the set of PVs, be an arbitrary set. Okay, so this is PV such that V is in script V. Okay, so we're going to state a bound that will work even if these PVs are not 2 delta separated, but then of course we need to correct some of the other terms that show up in the bound. This is based on a version of Fanos inequality that replaces the error probabilities, which we saw in the first lecture, probability that x comes from PV to the n, psi of x is not equal to V, by tail probabilities. Probability x comes from PV to the n, rho V psi of x V is bigger than T for some metric on, rho V on the set V. Okay. So this is not something that's specific to differential privacy. This is just another version of a lower bound you could prove that generalizes Fanos' lower bound. And I'm being a bit loose when I say Fanos method versus Fanos inequality. If you remember, Fanos method for minimax lower bounds depends on turning things into a decoding problem. And then what shows up is these sorts of quantities. What's the probability that my detector chooses the wrong thing when the data come from B? So there's, and so Fanos inequality, the usual Fanos inequality gives a lower bound for this. There's also a version that you could derive where instead of these inequalities, you look at something in terms of the probability that the distance is bigger than T. Now, in the case when T is equal to 0, then this is going to be exactly equal to the probability of being wrong. Okay, but we can, right? Okay, so so just a little bit more notation. So for each T bigger than 0, define the neighborhood size. Define the neighborhood size, which is NT is defined as the max over V in script V of the size of the set V prime in V such that rho V of V prime is less than or equal to T. So let me just write these things out and you can stare at them. And the separation function delta of T is equal to 1/2 minimum of rho of theta of PV, theta of PV prime, such that V and V prime are in script V, and rho sub V of VV prime is bigger than T. Okay, so what you want to think about is is when you have the case t equals 0, because that should be the usual Fanos inequality. In that case, the neighborhood size is just 1. So nt is the number of points which are within some radius of the point in question. And also, so if t is equal to 0, then you'll see that that this is the delta that leads to the 2 delta separation of the theta of PVs. Let me erase this because that didn't help. Okay, so the result is, so the distance-based version of the lower bound on minimax risk is phi of delta of t times 1 minus mutual information between x and v plus 1 divided by log base 2 of the size of the set divided by nt, where v is an index chosen uniformly over the set V, and x is distributed as p sub v. Okay, so right. So again, comparing this to the usual Fanos method, would have nt is equal to 1. So everyone would be well separated. There would only be one guy in each neighborhood set. Then we would just have a log of the size of the set. And everything would be 2 delta separated. So we would just have phi of delta there. But then what happens is, because we're not forcing the points to be well separated, we lose a factor of v over nt in the denominator. Well, hopefully I haven't completely confused everybody by now, but so this is a statement that holds for differential privacy, for general minimax lower bounds. And now I'll state the theorem from Ducci. So here's the theorem. And the theorem says that the locally differential private minimax risk satisfies R sub LDP of P L alpha is bigger than or equal to phi of delta of t times 1 minus n e to the alpha minus 1 squared over log base 2 of the set multiplied by another factor, which is also complicated, soup over all functions which are uniformly bounded by 1. I need to move this over again. Let's do this. Greater than or equal to this guy. V squared of gamma minus 1 over log base 2 of this guy, where we define where phi v, which maps all of the bounded functions on x to R, is defined via phi v of gamma equals integral over x, gamma of x times dpv of x minus dp bar of x, where, as you might imagine, p bar is the mixture of all of the distributions in our set. Okay, so just a couple comments and then let's take the break. So this expression probably looks really, really ugly, but what I want you to do is to compare this expression with the version of Fanos method that I stated up here, right? So you'll see that, that this quantity is basically this quantity, except instead of this mutual information bound, I have what's written here. Okay, so really there are kind of two components to proving this result. So the first one is to show that that the distance-based version of Fano is valid for minimax bounds. And so this is actually a paper that I think Ducci, Wainwright, and Jordan had maybe a few months before the paper on local differential privacy came out. So And then after that, to show that for LDP mechanisms, so in that case, you're observing not X, but you're observing Z, right? So Z is the locally differentially private processed version of X. And what you want to show is that you can actually write an upper bound on I of ZX, where, well, in terms of something, and the something will have, of course, something about the distribution of X under the possible PVs that are showing up in the set that you've constructed. And then what pops out as well is extra factors of e to the alpha. Okay, so I think I'm not going to go over the proof because I want to discuss how this is used in an example. So let's just end here for now, and then maybe I'll take questions and then we can take a break and I'll keep going.
Great, thanks, Po-Ling. Yeah, I guess there's, let's take a few questions if there are any. If you have a question, I'll run over and bring the mic to you. Yeah.
I was just curious on when you consider epsilon delta differential privacy notion that you introduced earlier, like for the very basic setup, how does the lower bound change?
Yeah, so well, maybe the easy answer is that you can actually show that the same lower bound will hold as long as delta isn't too big. So this lower bound is up here, and I think, oh, well, okay, so now it's going to be a different delta, but the same lower bound will hold as long as the delta that's used to, so let's call it green delta. So as long as the green delta is order of 1 over m, then you should end up with the same bound. And that's because when we're, well, how do we use the epsilon differential privacy? It's in using this Hamming, the fact that if the Hamming distance is small, then the probabilities don't change too much. So when you go down to the derivation, then we wanted to say that the probabilities don't change too much. So you'll get an extra slop of this delta term. So as long as delta isn't too small, then it doesn't change the bound too much. Okay, but that's a limitation of Fanos method. So as discussed by the authors, by Acharya et al. In their paper, this doesn't work if delta is larger, and so they advocate using the other versions of the bounds. So their paper is called Aswad, Fano, and the PAM, and they show how I think a differentially private analog of Aswad can be used when delta is larger.
Great. Any other questions? Perfect. So yeah, let's take our break. It looks like it's 10:39, so let's be back here at 10:59. Thanks again, Po-Ling.
All right.